The conference room in Tokyo's Naval Ministry building fell silent as Captain Tamechi Hara finished his intelligence briefing. It was November 1943, and the news was uniformly bad. American forces were advancing across the Central Pacific at a pace that seemed impossible just months earlier. But what caught Admiral Minechi Koga's attention wasn't the territorial losses. It was a single number in Hara's report that seemed absurd. "You're telling me," Koga said slowly, leaning forward over the mahogany table, "that American intelligence suggests each of these new Essex-class carriers can operate 90 aircraft." Hara nodded, his expression grave. "Perhaps more, sir. Some reports indicate up to 100 aircraft per vessel during surge operations." The room erupted in skeptical murmurs. Admiral Jisaburo Ozawa, one of Japan's most experienced carrier commanders, shook his head dismissively. "Impossible. Our largest fleet carriers, Akagi Kaga, operated 70 aircraft maximum. The laws of physics don't change because you're American. Deck space, hangar capacity, fuel storage, and ordnance handling these factors impose absolute limits." What Ozawa and his colleagues didn't understand was that American naval architects had fundamentally reimagined carrier design. While Japanese carriers were converted battlecruiser hulls or vessels designed in the 1920 seconds under treaty restrictions, the Essex-class represented a clean-sheet design, optimized for maximum aircraft capacity within a hull that could be mass-produced in American shipyards. The numbers that seemed impossible to Japanese admirals were not only possible, they were conservative estimates. Construction of USS Essex, the lead ship of her class, began at Newport News Shipbuilding on the 28th of April 1941. The design incorporated lessons from earlier American carriers, while introducing revolutionary features that would transform naval aviation. The Essex-class measured 872 feet in length overall, with a beam of 93 feet and a flight deck width of 147 feet. Standard displacement was 27,100 tons, reaching 33,400 tons at full load. This made Essex-class carriers significantly smaller than Japanese fleet carriers like Shokaku and Zuikaku, which displaced over 29,000 tons standard. Yet, through brilliant internal arrangement and operational procedures, Essex-class carriers routinely operated more aircraft than their larger Japanese counterparts. The secret lay in several interconnected design features that Japanese naval architects had either rejected or never considered. The Essex-class hangar deck was 654 feet long and 70 feet wide, providing 45,780 square feet of covered storage space. But unlike Japanese carriers, which stored all aircraft in the hangar when not in use, American doctrine called for parking aircraft on the flight deck permanently. The flight deck itself became operational storage space. American deck crews developed intricate aircraft spotting patterns that maximized the number of planes that could be positioned on deck while still allowing launch and recovery operations. During combat operations, an Essex-class carrier typically kept 30 to 40 aircraft spotted on the flight deck, with another 50 to 60 inches the hangar below. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. Japanese carriers couldn't replicate this approach because of a fundamental design difference. Japanese carrier flight decks were not armored and were not considered structural elements of the ship. They were essentially wooden platforms laid over the hangar, designed to be as light as possible to preserve stability and speed. Parking heavily loaded aircraft permanently on these decks would have caused structural problems and created dangerous congestion. Essex-class carriers used steel flight decks that were integral to the ship's structure. These decks could support the weight of fully loaded aircraft parked anywhere on the surface. American damage control doctrine also differed fundamentally from Japanese practices. American carriers used multiple redundant systems and extensive compartmentalization. An Essex-class carrier could absorb tremendous damage and remain operational because critical systems had backups and alternate routing. The power plant consisted of 8 Babcock and Wilcox boilers, generating steam for 4 Westinghouse-geared turbines, producing 150,000 shaft horsepower. This drove the 27,000-ton hull to a maximum speed of 33 knots with remarkable efficiency. The radius of action at 15 knots was 20,000 nautical miles, giving Essex-class carriers unprecedented strategic mobility. Aviation fuel capacity was equally impressive. Each Essex-class carrier could carry 240,000 gallons of aviation gasoline, enough to support sustained flight operations for weeks without refueling. Japanese carriers carried significantly less aviation fuel, requiring more frequent replenishment from oilers that were increasingly vulnerable to American submarines. The ordnance handling systems represented another revolutionary advance. Essex-class carriers used 8 aircraft elevators, 3 deck-edge elevators, and 2 centerline elevators. Deck-edge elevators, positioned outside the hull's armor box, could operate even when the hangar was damaged or filled with smoke. They also didn't interrupt flight deck operations when raising or lowering aircraft. Japanese carriers used only centerline elevators that penetrated the flight deck. When elevators were in use, they created obstacles that restricted flight operations. American deck-edge elevators eliminated this constraint, allowing simultaneous launch, recovery, and aircraft movement between hangar and flight deck. The ordnance magazines and bomb assembly rooms were positioned directly beneath the hangar deck, connected by dedicated ammunition elevators. Ordnance crews could arm aircraft in the hangar or on the flight deck with minimal handling time. This arrangement enabled Essex-class carriers to rearm and refuel entire strike groups in under 2 hours, a pace Japanese carriers couldn't match. Flight deck crews numbered over 300 men, organized into specialized teams with color-coded uniforms. Plane directors wore yellow jerseys, catapult and arresting gear crews wore green, ordnance handlers wore red, fuel handlers wore purple. This color-coding system eliminated confusion during high-tempo operations and allowed air bosses to manage deck operations visually. Training and doctrine multiplied these hardware advantages. American carrier pilots and deck crews trained continuously, developing procedures and reflexes that became automatic under combat stress. The Bureau of Aeronautics maintained standardized procedures across all carriers, meaning pilots and aircrew could transfer between ships without retraining. When USS Essex commissioned on December 31, 1942, her air group consisted of 36 F-6F Hellcat fighters, 36 SB-2C Helldiver dive bombers, and 18 TBF Avenger torpedo bombers, a total of 90 aircraft. This was the standard Essex-class air group composition for most of 1943 and early 1944. Japanese admirals who saw these numbers in intelligence reports assumed they represented theoretical maximums that could never be sustained in combat. They were catastrophically wrong. During the Battle of the Philippine Sea in June 1944, Essex-class carriers routinely launched and recovered strike groups of 70 to 80 aircraft while maintaining combat air patrol and anti-submarine patrols. The sustained sortie generation rate, the number of combat missions flown per day, exceeded anything Japanese carriers had achieved even during their most successful early war operations. Admiral Ozawa commanded Japanese carrier forces during the Philippine Sea battle. His 4 remaining fleet carriers and 5 light carriers embarked a total of 430 aircraft. The 9 American carriers opposing him operated over 900 aircraft, more than double Ozawa's strength. But the numerical disparity was even worse than it appeared, because American aircraft were superior in performance, American pilots were better trained, and American carriers could generate more sorties per day. The battle became known to American forces as the Great Marianas Turkey Shoot. Over 2 days, Japanese naval aviation was effectively destroyed. American pilots shot down approximately 600 Japanese aircraft while losing only 123 planes. 3 Japanese carriers were sunk. The remaining carriers returned to Japan with air groups so depleted they could no longer conduct offensive operations. Ozawa's after-action report was brutally honest. He described watching wave after wave of American aircraft appear over his task force, far more planes than his intelligence had suggested were possible. His own launches were pitiful by comparison, 60 to 70 aircraft per strike, which was the maximum his carriers could manage. The Americans were launching 150 aircraft strikes from positions over 200 miles away, something Ozawa had believed was operationally impossible. What Ozawa didn't know was that American carrier doctrine had evolved to treat multiple carriers as a single integrated striking force. Task Force 58, the American Fast Carrier Task Force, organized carriers into task groups of 3 to 4 carriers each. When launching a major strike, all carriers in a task group would spot and launch aircraft in coordinated sequence, combining their air groups into a single massive formation. An Essex-class carrier could spot approximately 40 aircraft on her flight deck for a launch. With proper wind conditions, all 40 aircraft could launch in under 15 minutes. If 3 Essex-class carriers launched simultaneously, 120 aircraft would be airborne in a quarter hour. The sheer density of this aerial armada was something Japanese forces had never encountered. Japanese carrier doctrine treated each carrier as an independent unit. Even when operating together, Japanese carriers launched separate strike groups that approached targets independently. This fragmented striking power and reduced effectiveness. American doctrine concentrated maximum force against single targets, overwhelming defenses through sheer numbers. The other factor Japanese admirals failed to anticipate was American industrial capacity. By late 1944, 17 Essex-class carriers were in commission with more under construction. Combined with 9 Independence-class light carriers and dozens of escort carriers, the U.S. Navy operated over 100 aircraft carriers of all types. Japan had 4 operational fleet carriers remaining. Admiral Koga, who had dismissed the intelligence about Essex-class capabilities in late 1943, was killed in March 1944 when his aircraft disappeared during a flight between bases. His successor, Admiral Soemu Toyoda, inherited a hopeless strategic situation. Japanese carrier, aviation had been gutted. Fuel shortages prevented realistic training for replacement pilots. The handful of carriers still operational lacked aircraft and aircrew to fill their hangar decks. Meanwhile, Essex-class carriers were appearing in the Pacific at a rate of nearly 2 per month. Each new carrier arrived with a fully trained air group, abundant spare parts, and logistical support that seemed limitless to Japanese observers. The industrial disparity was so overwhelming that rational resistance seemed futile. Yet Japanese naval leadership continued planning offensive operations as if parity might somehow be restored. This cognitive dissonance, the inability to accept that the war was lost, would lead directly to catastrophes like Operation Tengo, Yamato's suicide mission, where Japanese forces were sent to certain destruction not for military necessity, but to preserve institutional honor. The Essex-class carriers that Japanese admirals never expected would launch 90 planes per ship didn't just meet that standard, they exceeded it repeatedly, generating sortie rates that even American pre-war planning had considered optimistic. These ships, produced in numbers that seemed impossible to Japan's resource-starved navy, rewrote the rules of naval warfare and sealed the outcome of the Pacific War. The mathematics were straightforward and terrifying. In 1941, the United States laid down keels for 7 Essex-class aircraft carriers simultaneously at 4 different shipyards. Japan's entire naval construction capacity consisted of 4 major naval arsenals and a handful of private yards, most of which were committed to building battleships, cruisers, and destroyers. America was building more fleet carriers in a single year than Japan could construct in a decade. This disparity wasn't accidental. It was the result of fundamentally different approaches to industrial warfare. Japanese naval construction followed traditional methods refined over centuries. Each ship was a unique project, built by master craftsmen who fabricated components on-site using individual measurements and custom fitting. Quality was exceptional, but speed was sacrificed. Yamato required 4 years from keel laying to commissioning, Her sister ship Musashi took even longer. American shipbuilders approached carrier construction like automobile manufacturing, standardized components, modular assembly, maximum worker efficiency through specialized tasks. Newport News Shipbuilding, New York Naval Shipyard, Bethlehem Quincy, and Philadelphia Naval Shipyard all built Essex-class carriers using identical plans and interchangeable parts. The construction timeline was almost unbelievable. USS Essex was laid down on the 28th of April 1941, launched on the 31st of July 1942, and commissioned on the 31st of December 1942, 20 months from keel to combat readiness. USS Yorktown, CV-10, the second Essex-class carrier, required only 16 months from keel laying to commissioning. Later vessels were completed, even faster as construction techniques improved. Albert Etheridge worked as a welding supervisor at Newport News during the Essex-class construction program. In a 1982 oral history, he described the organized chaos of carrier construction. We had 3 shifts running 24 hours. At peak, over 8,000 workers on a single carrier. The thing that made it possible was modularity. We weren't building one ship, we were building hundreds of identical sections that got assembled into a ship. The hull was constructed in massive prefabricated sections, each containing complete frames, deck sections, bulkheads, and often pre-installed piping and electrical conduits. These sections were built in fabrication shops, adjacent to the building ways, then lifted by cranes and welded into position. A section weighing 200 tons could be positioned and secured in hours. Traditional Japanese construction methods built hulls from the keel up, frame by frame, plate by plate. It was precise but glacially slow. American modular construction meant multiple sections could be built simultaneously in different shops, then assembled rapidly once the keel was laid. The time savings were enormous. Welding was critical. Japanese shipyards still relied heavily on riveting, which was labor-intensive and time-consuming. American yards used advanced electric arc welding techniques throughout. Welded seams were stronger, lighter, and faster to complete than riveted joints. Essex-class carriers used approximately 5,000 tons of welding electrodes per ship, evidence of the scale of welded construction. The flight deck posed unique challenges. Each Essex-class flight deck was 8.62 feet long and consisted of 3-inch steel plate laid over supporting beams. The deck had to be perfectly flat, any deviation would interfere with landing operations. Achieving this precision while welding together dozens of massive steel plates required innovative techniques. Workers used jigs and fixtures that held deck sections in perfect alignment while welds cooled. Multiple welding crews worked simultaneously on different sections, following strict sequences to prevent warping from uneven thermal expansion. The result was a flight deck with surface tolerance measured in fractions of an inch over 800 feet, an extraordinary achievement in mass production. The hangar deck presented different problems. This space had to be completely open, 654 feet long and 70 feet wide, with no supporting columns that would interfere with aircraft movement. Supporting this massive open space while maintaining structural strength required sophisticated engineering. The solution was a system of transverse and longitudinal beams that distributed loads to the hull structure, creating a rigid platform that could support the flight deck above while leaving the hangar clear. Engine installation was another milestone that demonstrated American industrial capability. Each Essex-class carrier required 4 massive Westinghouse steam turbines, each weighing over 200 tons, plus 8 boilers and associated pumping, piping, and control systems. The entire propulsion system, boilers, turbines, reduction gears, shafts, and screws, was installed as a series of prefabricated modules. Boilers arrived from manufacturers as complete units, tested and certified. They were lowered through openings in the deck, positioned, and connected to pre-installed piping. The turbines similarly arrived as finished assemblies. This modular approach meant the propulsion system could be installed and tested in weeks rather than months. Electrical systems were equally impressive. An Essex-class carrier required over 3,000 miles of electrical cable connecting thousands of components, lighting, communications, fire control, damage control, ventilation, pumps, elevators, catapults, and countless other systems. Installing this wiring using traditional methods would have taken years. American electrical engineers designed standardized wiring harnesses pre-assembled bundles of cables with connectors already installed. These harnesses were manufactured off-site, tested, then installed in hull sections before assembly. When sections were joined, connectors plugged together, completing circuits without extensive on-site wiring work. Quality control was rigorous despite the speed. Each section underwent inspection before joining. Welds were X-rayed to detect hidden flaws. Piping systems were pressure tested. Electrical systems were tested using standardized procedures. Ships underwent extensive trials before commissioning, including aircraft compatibility testing, damage control drills, and high-speed runs to verify propulsion performance. The human dimension was equally important. Shipyard workers were trained in specialized schools established by major yards and the Navy. Welders attended multi-week programs teaching carrier-specific techniques. Electricians learned to read complex wiring diagrams and work with the particular systems used in Essex-class construction. This investment in training paid enormous dividends in construction speed and quality. Women entered the shipbuilding workforce in unprecedented numbers. By 1943, over 30% of shipyard workers were female, taking positions as welders, electricians, pipe fitters, and crane operators jobs that had been male-only before the war. Their contribution was essential to maintaining construction rates, even as male workers were drafted into military service. The supply chain supporting carrier construction was a logistics marvel. Steel mills prioritized naval contracts, delivering thousands of tons of specialized plate and structural steel on precise schedules. Manufacturers produced turbines, boilers, radar systems, catapults, arresting gear, and thousands of other components in quantities that would have seemed impossible in peacetime. Aircraft manufacturers coordinated their production with shipyard schedules. When a carrier neared completion, her air group's aircraft were already in production or delivered to training squadrons. By commissioning day, a full air group of 90 aircraft was ready to embark, along with spare parts, ordnance, and all necessary support equipment. The cost was substantial but manageable within America's wartime economy. Each Essex-class carrier cost approximately $78 million to construct, equivalent to about $1.4 billion in 2024 dollars. For that price, the Navy received a platform that could operate 90 aircraft, steam at 33 knots for 20,000 miles, absorb battle damage that would sink lesser ships, and remain in service for decades. Japan lacked the industrial capacity to replicate this achievement. Japanese steel production in 1943 was 7.8 million tons annually, less than half of what American mills produced in a single month. Japan's electrical generating capacity, machine tool production, and shipbuilding capacity were similarly insufficient for mass production of complex warships. More fundamentally, Japanese industrial culture was oriented toward craftsmanship rather than mass production. The notion of building carriers on assembly lines using interchangeable parts was philosophically alien to Japanese naval architects, who prided themselves on building each ship as a unique masterpiece. Preparing and narrating this story took us a lot of time, so if you are enjoying it, like this video, it means a lot to us. Now back to the story. By August 1945, the U.S. Navy had commissioned 17 Essex-class fleet carriers, with 7 more under construction. The Independence-class light carrier program, using cruiser hulls, produced 9 carriers even faster, some commissioned within 14 months of keel laying. The Casablanca-class escort carrier program built 50 carriers in under 2 years, using prefabricated merchant ship hulls. Japanese shipyards completed no new fleet carriers after 1944. The carrier Shinano, converted from a Yamato-class battleship hull, was commissioned. in November 1944 and sunk by an American submarine 10 days later on her maiden voyage. No other Japanese fleet carriers reached completion before the war ended. The industrial disparity was so complete that Japanese naval planners stopped trying to match American production and instead focused on kamikaze tactics, trading pilots' lives for ships, because Japan could replace pilots more easily than America could replace carriers. This calculation proved wrong. America was producing carriers faster than kamikaze attacks could sink them, while Japan's pilot training programs collapsed under fuel shortages and American air attacks on training bases. Admiral Isoroku Yamamoto had warned before Pearl Harbor that Japan could run wild for 6 months to a year, but couldn't win a prolonged war against America's industrial might. The Essex-class construction program proved Yamamoto's prophecy with brutal efficiency. 20 months from keel to combat, that was the assembly line rhythm that built an armada and crushed an empire. The 7th of April 1945, 1,000 hours. The flight deck of USS Essex trembled as 40 aircraft roared into the sky in rapid succession. 40 seconds per launch, that was the tempo Essex's deck crew had perfected through 2 years of Pacific combat. F-6F Hellcat fighters went first, accelerating down the deck and climbing into formation. SB-2C Helldiver dive bombers followed, heavier and slower but airborne within their allocated time window. Finally, TBM Avenger torpedo bombers lumbered into the air, each carrying a Mark 13 torpedo slung beneath the fuselage. 10 minutes after the first fighter launched, all 40 aircraft were airborne and forming up. USS Bennington, USS Belleau Wood, and USS San Jacinto were launching simultaneously. Within 30 minutes, over 150 aircraft from Task Group 58.3 were orbiting in massive formations, preparing to strike Yamato. Lieutenant Commander Robert E. Riera led Essex's strike group. As the formation climbed through broken clouds toward 10,000 feet, Riera checked his fuel gauges and navigation. The target was 280 miles away, a long flight even under good conditions. Weather was deteriorating, with low clouds and intermittent rain squalls reducing visibility. Some strike groups would get lost in the weather and never find the Japanese force, but Riera's navigation was precise. At 1,230 hours, the formation broke through clouds and spotted Yamato's distinctive pagoda superstructure 15 miles ahead. The battleship was turning in wide circles, her escorting destroyers arranged in a defensive ring. Riera transmitted coordinates to the trailing formations and began organizing the attack. American carrier doctrine called for coordinated attacks using all 3 aircraft types simultaneously. Fighters would strafe anti-aircraft positions and provide cover. Dive bombers would attack from high altitude, forcing the target to maneuver. Torpedo bombers would attack from multiple directions at low altitude, forcing the target to choose which threats to counter. The goal was to overwhelm the enemy's ability to respond. No ship could simultaneously evade dive bombers, torpedo bombers, and concentrate anti-aircraft fire in multiple directions. Something would get through. Yamato opened fire at 1,232 with her main battery guns, firing special anti-aircraft shells that burst into clouds of steel fragments. The massive gun blasts were impressive, but ineffective. American aircraft simply flew through the explosions untouched. Riera noted this in his after-action report. The battleship fired its main battery guns at our aircraft. These produced large black bursts but caused no damage. The ship's AA fire was intense but poorly coordinated. At 1,237, Riera pushed over into his attack dive. The Helldiver fell through 8,000 feet in a near-vertical descent, building speed toward 300 knots. Yamato grew larger in the bomb sight, her deck guns firing streams of tracers that arced through the air like hoses spraying luminous water. At 2,500 feet, Riera released a 1,000-pound armor-piercing bomb separated from the centerline rack and fell away. Pull-out forces pressed Riera into his seat as the Helldiver bottomed out at 1,500 feet and climbed away. Behind him, other dive bombers were descending in sequence, releasing bombs every few seconds. Fountains of water erupted around Yamato as near misses detonated. Direct hits sent smoke and debris flying from the battleship's superstructure. While the dive bombers attacked, Lieutenant George P. Mopin led his torpedo bomber section in from the port side. Avengers approached at wave-top height 50 feet above the waves, sometimes lower where Yamato's high-angle anti-aircraft guns couldn't depress far enough to engage them. The low altitude made torpedo bombers vulnerable to smaller caliber weapons, but it was the only approach that worked. Maupin's section bore in at 200 knots, maintaining formation despite intense fire. Two Avengers were hit, one burst into flames and cartwheeled into the sea. The other struggled to maintain altitude with one engine damaged. At 1,000 yards, Maupin fired his torpedo. The Mark 13 dropped cleanly, entered the water, and ran straight toward Yamato's hull. 11 seconds later, a massive underwater explosion sent a column of water 200 feet into the air alongside Yamato's port side. The torpedo had struck beneath the waterline near the engine rooms. Maupin climbed away, watching other torpedo bombers make their runs. More torpedoes entered the water, leaving white wakes as they tracked toward the battleship. The coordination was devastating. Yamato was turning to avoid torpedoes from one direction, while dive bombers attacked from above and torpedo bombers attacked from different angles. Her anti-aircraft guns were firing in all directions, but the sheer number of attackers ensured that most aircraft completed their runs successfully. Essex's strike group withdrew after expending ordnance, but the attack was far from over. Task Group 58.1 had launched 80 aircraft that arrived 20 minutes after the first wave. These fresh attackers found Yamato already damaged, listing and slowing. They pressed home attacks with the same methodical efficiency. Lieutenant Thomas H. Reedy led a division of Hellcats from USS Hornet in a strafing attack that killed dozens of Japanese anti-aircraft gunners. The deck was covered with men, Reedy reported. We made repeated strafing runs until our ammunition was expended. The effect was devastating. Eliminating the AA crews allowed following torpedo bombers to make their attacks with fewer losses. The second wave concentrated all torpedo attacks on Yamato's port side. This was deliberate by flooding compartments on only one side. Attackers could accelerate capsizing. Yamato's damage control teams were attempting to correct the port list by counter-flooding starboard compartments, but incoming torpedoes were hitting faster than counter-flooding could compensate. At 1,302, Task Group 58.4 arrived with 110 additional aircraft. Yamato was now under continuous attack by over 200 aircraft operating in coordinated groups. The battleship was burning, listing, and had lost steering control. She was turning in slow circles, still firing but clearly doomed. Lieutenant Commander John C. Eldridge led torpedo bombers from USS Yorktown in the final attacks. The ship was already heavily damaged, Eldridge reported. She was listing badly to port and moving slowly. We made coordinated attacks from multiple directions. I observed at least 4 torpedo hits during our attack run. The mathematics that Japanese admirals had refused to accept were playing out with brutal clarity. Yamato mounted 162 anti-aircraft guns and was still firing almost all of them when she capsized. But 162 guns could not create enough defensive fire to stop 280 attacking aircraft operating under professional coordination. The loss ratio demonstrated the disparity. American forces lost 10 aircraft and 12 aircrew. Yamato's 3,332 crew members included only 276 survivors. This 2.78-to-1 casualty ratio wasn't the result of superior courage or fighting spirit. It was the mathematical outcome of overwhelming force applied with systematic efficiency. Back aboard Essex, Riera and his fellow pilots attended debriefing sessions where intelligence officers compiled detailed after-action reports. Strike photos were developed and analyzed. Gun camera footage was reviewed. Every detail was recorded: which torpedo bomber squadrons achieved hits, which dive bombing attacks were most effective, what defensive tactics the Japanese employed, how effective American coordination had been. This systematic analysis would inform future operations. The lessons from sinking Yamato were compiled into tactical bulletins distributed throughout the fleet. Future carrier strikes would incorporate refinements based on April 7's experience. For Essex and her air group, the mission was noteworthy but not exceptional. The carrier had participated in strikes against Japanese targets from the Marshalls to Okinawa, launching thousands of sorties over 2 years. Sinking Yamato was satisfying the biggest target the air group had ever attacked, but the fundamental operation was identical to dozens of previous strikes. Launch 40 aircraft in 10 minutes. Form up. Navigate to target. Coordinate attack. Return to carrier. Land. Rearm. Repeat. This cycle had been executed so many times that it was routine. The professionalism was what won wars. Japanese admirals had never expected Essex-class carriers to launch 90 aircraft. They were catastrophically wrong. Essex routinely launched 70 to 80 aircraft per strike, recovered them, rearmed and refueled the entire air group, and launched again within 3 hours. During the Battle of Leyte Gulf, Essex's air group flew 130 sorties in a single day, exceeding the number of aircraft Japanese carriers could embark, let alone launch. The 17 Essex-class carriers that served in World War II operated a combined total of over 1,500 aircraft. Task Force 58 at its peak operated 1,200 aircraft from 16 carriers. This aerial armada could strike targets 300 miles away, with hundreds of aircraft in coordinated waves that no defense could stop. When Yamato exploded at 1,423 on the 7th of April 1945, she took with her not just 3,000 men, but the last illusions that battleships remained relevant in modern naval warfare. The Essex-class carriers that had launched the killing blow represented a new paradigm, one that Japanese admirals had failed to recognize until far too late. The mathematics were simple and terrible. One Essex-class carrier launching 90 aircraft was more combat effective than any battleship ever built. 17 Essex-class carriers launching over 1,500 aircraft represented power that no surface fleet could contest. The age of the battleship ended in fire and explosion on April 7th. What replaced it was the age of the American Fast Carrier Task Force and its most capable representative, the Essex-class, whose 90 aircraft air groups had seemed impossible to Japanese admirals until they became the instrument of Japan's naval destruction. The smoking room at the Naval War College in Newport, Rhode Island, filled with tension as Captain Joseph J. Jocko Clark faced a panel of senior admirals in March 1946. Clark had commanded USS Yorktown, CV-10, an Essex-class carrier, through some of the Pacific War's most intense operations. Now, 6 months after Japan's surrender, the Navy was conducting exhaustive reviews of wartime performance to inform future doctrine. Captain Clark, Admiral Raymond Spruance, began, "Your after-action reports consistently describe launching strike groups exceeding 90 aircraft from Yorktown. Some skeptics in this room believe those numbers are exaggerated. Please clarify for the record." Clark didn't hesitate. "Admiral, 90 aircraft was our standard strike package. During the Philippine Sea operation in June 44, we launched 93 aircraft in one strike. At Leyte Gulf, we launched 104 aircraft in a single day across multiple strikes. The Essex-class wasn't designed to launch 90 aircraft, it was designed to exceed that number routinely." The Admiral to Spruance's left, a battleship officer who had watched his weapon system become obsolete, shook his head. "The hangar specifications show capacity for 82 aircraft maximum. Where did these extra planes come from?" Clark smiled slightly. "The hangar was never meant to hold our entire air group, sir. We parked 30 to 40 aircraft on the flight deck permanently. During extended operations, we sometimes had 110 aircraft aboard 90 in the air group plus 20 operational spares. The Japanese never understood this because they stored everything below deck. We turned the flight deck into a parking lot and it changed everything. This fundamental doctrinal difference, one that Japanese admirals had failed to grasp until their carrier force was destroyed, represented the true genius of Essex-class design. The ship wasn't revolutionary because of any single feature. It was revolutionary because every system was optimized for sustained high-tempo air operations that no previous carrier could match. The air group organization reflected this philosophy. In 1943, the standard Essex Air Group consisted of VF-1 Fighter Squadron with 36 F-6F Hellcats, VB-1 Bombing Squadron with 36 SB-2C Helldivers, and VT-1 Torpedo Squadron with 18 TBM Avengers. This 3-6-3-6-1-8 composition provided balanced striking power for any target enemy carriers, battleships, land installations, or submarine bases. By late 1944, as Japanese air power collapsed and American forces shifted towards supporting amphibious operations, air group composition evolved. Fighter squadrons expanded to 73 aircraft, while dive bomber squadrons shrank or were eliminated entirely. The new fighter-heavy air groups could maintain continuous combat air patrols over invasion beaches while still launching large strike groups against inland targets. This flexibility was impossible for Japanese carriers. Their smaller air groups and limited deck space meant they couldn't adjust composition without completely reorganizing their air wings, a process requiring weeks in port. Essex-class carriers could embark different aircraft types, reconfigure air groups, and return to operations within days. The operational tempo achieved by Essex-class carriers would have seemed impossible before the war. During the Fast Carrier Task Force raids on Tokyo in February 1945, USS Essex launched 6 separate strike groups over 18 hours, 482 total sorties from a single carrier. The deck never stopped moving. Aircraft launched, others landed, crews rearmed and refueled planes, then launched again in an endless cycle. Lieutenant Henry Miller served as air boss aboard USS Hancock during these operations. In his 1947 memoir, he described the organized chaos. We had color-coded teams handling every function, yellow shirts directing aircraft movement, green shirts on catapults and arresting gear, purple shirts fueling, red shirts loading ordnance. Everyone knew their job so perfectly that we didn't need verbal communication. The air boss gave hand signals, teams executed instantly. We could turn around a 30-plane strike group, recover, rearm, refuel, relaunch in 90 minutes. This performance level required more than good design. It demanded superbly trained personnel operating with machine-like precision. American carrier training programs, established before the war and expanded dramatically afterward, produced crews that could execute complex operations instinctively under combat stress. Pilots trained for 18 months before joining fleet squadrons. They accumulated 300 flight hours, including 7-5 carrier, landing practice sessions on training carriers in Chesapeake Bay. By the time a pilot reached a combat squadron, carrier landings were routine. Japanese pilot training programs, crippled by fuel shortages after 1943, produced barely qualified pilots with 100 total flight hours who often had never landed on a carrier before joining their units. Deck crew training was equally rigorous. Sailors attended specialized schools teaching proper procedures for their specific roles. Ordnance handlers learned to arm 12 different weapons types. Fuel handlers learned gravity refueling systems, pressure refueling systems, and emergency defueling procedures. Catapult operators learned to calculate launch parameters for different aircraft weights and wind conditions. This training investment paid enormous dividends. USS Essex's deck crew could arm and launch 40 aircraft in 12 minutes. Japanese carriers required 40 minutes for the same operation. Over a 12-hour combat day, This efficiency difference meant American carriers could launch 3 times as many strike groups as Japanese carriers of similar size. The maintenance capacity was equally impressive. Each Essex-class carrier embarked complete maintenance shops, including machine shops, electronics repair facilities, ordnance workshops, and aircraft engine overhaul capabilities. Carriers could perform repairs at sea that Japanese carriers required dockyard support to accomplish. During the Philippines campaign, USS Intrepid was hit by a kamikaze that destroyed 6 aircraft on the flight deck and killed 69 crew members. The ship withdrew from the combat zone, made temporary repairs while underway, and returned to operations within 48 hours. A Japanese carrier suffering equivalent damage would have required months of dockyard repairs. The damage control systems represented another critical advantage. Essex-class carriers used British innovations in compartmentalization combined with American Togay's advancements in firefighting equipment. The result was ships that could absorb catastrophic damage and survive. USS Franklin was hit by 2 armor-piercing bombs in March 1945 while operating 50 miles off Japan. The bombs penetrated deep into the ship before exploding, triggering massive fires and secondary explosions that killed 724 crew members. Ordinarily, such damage would doom any ship, but Franklin's damage control teams contained the fires, kept the engineering spaces operational, and the ship reached port under her own power. She was repaired and returned to service before the war ended. Japanese carriers couldn't survive comparable damage. Carrier Taiho, one of Japan's newest and most heavily armoured carriers, was hit by a single torpedo during the Philippine Sea Battle. The torpedo ruptured aviation fuel tanks, and gasoline vapours spread through the ship. 6 hours later, a spark ignited the vapours, triggering an explosion that destroyed Taiho completely. Poor damage control. Doctrine opening ventilation systems that spread vapours rather than containing them had turned survivable damage into catastrophic loss. The strategic mobility of Essex-class carriers extended their dominance beyond combat operations. The 20,000-mile range at cruising speed meant Task Force 58 could operate anywhere in the Pacific without establishing forward bases. Japanese carriers, with shorter range and chronic fuel shortages, were tethered to fleet oilers that were increasingly vulnerable to American submarines. During the Okinawa campaign, Task Force 58 operated continuously for 92 days, launching strikes, maintaining combat air patrols, and defending against kamikaze attacks without returning to port. Underway replenishment ships provided fuel, ammunition, spare parts, and replacement aircraft at sea. This sustained operational presence would have been impossible for Japanese carrier forces even before their catastrophic 1944 losses. The night operations capability gave Essex-class carriers another decisive advantage. By 1944, specialized night fighter squadrons operating F-6, F-5 Newtons. Hellcats with radar could intercept Japanese aircraft in total darkness. Night-qualified landing signal officers could recover aircraft after dark using specialized lighting systems. Essex-class carriers could literally operate around the clock. Japanese carriers lacked radar-equipped night fighters, night landing capabilities, or pilots trained for night operations. After sunset, Japanese carriers were defenseless against air attack and couldn't launch strikes. American carriers exploited this vulnerability repeatedly, launching dusk and night strikes that caught Japanese forces unable to respond. The final measure of Essex-class effectiveness came in the carrier's extraordinary service life. Most Essex-class carriers remained in active service for decades after World War II ended. They were modernized repeatedly, receiving angled flight decks, steam catapults, improved arresting gear, and new electronics. Several carriers served into the 1,970 operating jet aircraft that weighed 3 times more than World War II propeller planes. USS Lexington, CV-16, was decommissioned in 1991 after 49 years of service, the longest-serving aircraft carrier in naval history. This longevity was possible because the original design incorporated enough reserve displacement structural strength, and internal volume to accommodate decades of modifications without fundamental rebuilding. Japanese carriers that survived the war were scrapped immediately because their designs couldn't be modernized. They were optimized for 1,930 seconds aircraft and doctrine, with no capacity for evolution. Essex-class carriers were built with enough margin to evolve through 4 generations of aircraft and 3 generations of naval warfare doctrine. By 1946, when Captain Clark testified at Newport, the evidence was overwhelming. Essex-class carriers had operated aircraft in numbers Japanese admirals considered impossible. They had sustained sortie rates Japanese carriers couldn't approach. They had absorbed battle damage that would have sunk Japanese carriers. They had operated continuously in forward areas where Japanese carriers required constant port time. The 17 Essex-class carriers, commissioned during World War II, accumulated 1,045,501 combat sorties, dropped 299,827 tons of bombs, fired 72,479 rockets, and launched 21,525 torpedoes. These ships destroyed or contributed to the destruction of hundreds of Japanese vessels, thousands of aircraft, and countless shore installations. Their aircraft flew the majority of combat missions that strangled Japan's maritime logistics, isolated Japanese garrisons, and eventually bombed the Japanese home islands into submission. Admiral Spruance concluded the Newport session with a question that would shape naval doctrine for generations. Captain Clark, if you were designing the next generation of aircraft carriers, what would you change about the Essex-class? Clark considered carefully before answering. Sir, I'd make them bigger to accommodate heavier aircraft and increase aviation fuel capacity for sustained operations. But fundamentally, the Essex-class got the equation right: maximum aircraft capacity, maximum sortie generation rate, maximum operational endurance. That formula won the Pacific War. Any future carrier should follow the same philosophy, just scaled up for jet aircraft. The post-war supercarriers Forrestal-class, Kitty Hawk-class, and eventually the nuclear-powered Nimitz-class followed Clark's prescription exactly. They were enlarged, improved Essex-class carriers optimized for jet aircraft, but retaining the operational philosophy that made the Essex-class dominant. Japanese admirals had never expected Essex-class carriers to launch 90 aircraft per ship. They assumed such performance was impossible, that American claims were propaganda, that the laws of physics prevented any carrier from operating air groups that large at combat tempo. They were catastrophically, completely, definitively wrong. The Essex-class didn't just launch 90 aircraft. It exceeded that standard routinely, sustained combat operations indefinitely, absorbed damage that would sink lesser ships, and served for half a century. These 17 carriers and the 1,500 aircraft they operated didn't just win battles. They made Japanese defeat inevitable from the moment they entered service. The mathematics were never in doubt. Japanese admirals simply refused to accept them until American bombs and torpedoes, delivered from Essex-class flight decks, wrote the final equation in fire across the Pacific.